the cool thing about our PERT equation for exponential growth models is it actually goes the other way too. This will work great for decay models, which is when your substance is decreasing in size or value. This could be a population that's shrinking from starvation or something. It could be any number of things. One popular application is in radioactive substances, like we have in this example. So with that as an idea, let's go ahead and solve this thing. I'm going to take my equation down here. And let's take a look at what we're given. We're saying in 100 days, okay, that's a time right there. So I know right away that something is going on in 100 days. The radioactivity of a sample decreases by 18%. So what's decreasing? It's how much of a sample you have. You can think of radioactivity as your population, if you like. Whatever that is, decreased by 18%. So I don't know what P is, or P naught. Okay, I have no idea. And I don't know what rate is, but I do know that it's 100 days for my time. Now, you might think you don't know your final population either. How could you? You don't know your initial population. That's true, I don't know the exact number, but I do know that whatever it is 18% less than I started at. So 1 minus 0.18. Pause this for a second, convince yourself of that fact, because when you lose 18%, what that means is you have 82% left. So I have an equation that looks like this. 0.82 P naught equals P naught times R, or times E to the R to the 100. Now, what that means is I can cancel out my P naughts, and now I have this. This is very useful. 0.82 equals E to the 100R. I only see one variable in here. We can solve this using a natural logarithm. Okay, so I'm going to move that guy over, make some room for a log. And there we go, natural log. And this thing is going to turn very nice on the right side. It's going to be just 100R. The natural log and the E cancel each other out. So if I want rate, it's just going to be 1 over 100 times the ln of 0.82. And that'll be my rate, my decay rate per day. Now, it's going to be a small number. Okay, once you do this calculation, that's going to be, according to my calculator anyway, it is negative, because it's decay, 0.001985. I think I'll stop here. And remember, that's a decimal. It's not a percentage. And this thing wants a percentage. So go ahead and give it a percentage. Multiply it by 100. You get 0.1984, right? And you can put all decimals there if you want, but at some point you're going to have to round it. I would just suggest using a lot of decimals. 5, 6 decimals is a good number, because every time you round, you're going to make a small error. So keep that small. Next question, what is the half-life of the elements? Well, we're going to assume the same decay rate, right? We haven't changed our elements. And what we do there to calculate the half-life is actually pretty straightforward. Half-life means you've lost half your life, right? Half the radioactivity. So that means you have half, 50% of the initial value. So here's my equation now. And I know what R is. It's this thing. So if you plug that R value in here, look what we get. First of all, the P naughts cross out. You get 0.50, 50% equals, and we're going to take the ln of both sides. The ln of 0.5 equals R, which is, I'll just write the details here, equals RT. Remember, I took the natural log of the right side, it canceled out the E, and that equals negative 0.0019845 times T. So all I have to do at this stage is divide each side by this terrible decimal. So I get ln of 0.5 divided by negative 0.0019845. Carry all those decimals, and that's going to give you T, the half-life of your element. In other words, how long it takes to reach 50%. Now, as a sanity check, this better be longer than 100 days, because it took me 100 days to get to 82%. It's going to take longer to get to 50%. So that's a useful way to just check yourself and make sure that we're talking common sense here. And my calculator told me 349 days. Great. So that's that answer. And the last step is, how long will it take for a sample of 100 milligrams to decay to 27 milligrams? Okay, no problem. All this one is a very similar version of what I just did. So I'm not going to go through this all the way. I'll leave this for you to solve. But I will show you the equation we're going to set up here. Here's my PERT equation. And I'm told that I started with 27 milligrams. I ended with 27 milligrams, and I started with 100 milligrams. And then it's e to the RT. Well, what's R? Same thing it's been. 0.01985 times t. We're going to end up doing first a division by 100, then a natural log of both sides. It's the same exact procedure that you just did with the half-life, but now we're calculating a different life. This is the amount of time it takes to get to 27% instead of 50%. Okay?